So in this presentation, we will talk about helical ground heat exchanger. This project was funded by the California Energy Commission. And as Ali mentioned, my name is Antash Najib. I am a PhD student in the MAE department at UC Davis, and I'm a GSR at the Western Cooling Efficiency Center. So a brief outline of this presentation, there would be a short introduction to ground heat exchangers with special focus on the helical GHEs, or ground heat exchanger, which is the focus of this project. We'll look at the computational models that were used for this project, and then we will dive into the parametric study, which was done using one of these models. We'll take a quick look at ways to couple the model to Energy Plus, which is a building simulation software, and then we'll conclude the presentation. The basic idea behind GHE is using the ground as a sink or source instead of the ambient air. In summer, when the building needs cooling, the ground is cooler than the ambient air. In winter, when the building needs heating, the ground is warmer than the ambient air. So from a thermodynamic standpoint, operating a heat pump between the building and the ground leads to greater efficiency. Ground heat exchanger technology has been around for decades, and the figure on the left shows some of the designs and configurations available. The vertical GHE can have a depth up to 500 feet. However, this design faces some restrictions. First of all, because of the depth of the GHE, the excavation cost, which is usually the largest cost associated with the system, can be high. The design application is also limited based on geological conditions, as well as legal requirements around groundwater contamination issues. A workaround is the horizontal GHE or the slinky horizontal GHE, but these designs tend to require more land. A compromise between the depth and land requirement constraint is the large diameter shallow bore helical GHE, which is the focus of this project. The diameter can be up to 3 feet, whereas the depth can be up to 25 feet. The photographs on the right show the installation of this helical GHE at Honda Smart Home in Davis, California. Now, looking at the computational models used for this research, the first one is the capacitance resistance model, which was originally developed by Professor Angelo Zarella of University of Padova in Italy. It is a simplified model and is therefore computationally very efficient. We developed a CFD model, which is computationally more intense. However, it is highly detailed and provides a final resolution of the ground temperatures. Based on the results of the detailed CFD model, we were able to improve the simplified Karam model, and we were also able to validate the improved version of the model. The figures on the right side show the mesh of this CFD model. And as you can see, the mesh is quite dense, and we have about 6 million nodes in one particular model. Now let's look at how once we were able to improve and validate the simplified model, the simplified model was used for the parametric study, which we will look at now. Now, one thing to note is that these systems are, of course, coupled to heat pumps. The performance of the heat pump itself depends on the source side temperature and on the load side temperature. And we were able to work with Professor Zarella to incorporate this effect into the validated Karam model. We used CBEC-RES model to generate the building load profile in a typical year in 2 California climate zones. These were Sacramento and Riverside. We then performed a detailed parametric analysis by varying the following parameters: the spacing between the GHEs, which is the distance between 2 GHEs, the arrangement of the GHEs. In one configuration, we considered an L-shaped arrangement. In another, we looked at a grid arrangement. We varied the number of GHEs, and we also varied the borehole diameter and the helix height. Finally, we also varied the soil type. We also compared this to an air-sourced heat pump as a baseline to evaluate the benefits of the project. Now this figure shows the results of the parametric study for Sacramento. The first figure shows the ground heat exchanger cost in dollars, whereas the second figure shows the electricity consumed in kilowatt hours per year. And we can see that the air source system has also been shown here. Now, the first thing to understand is this reference case. The parameters for this reference case are given in this table. The spacing is 3.5 meters. The number of GHEs are 8. The diameter is 24 inch and the height is 20 feet. And the arrangement considered is L-shaped. Now we see when we change the spacing between the GHEs, there's no impact on cost. However, the performance improves slightly as the spacing is increased. When we change the number of GHEs, there's a significant impact, or proportional impact rather, on the ground heat exchanger cost. And the performance also changes. The more GHEs you have, the lower the electricity consumption. Now, when we change the diameter of the GHE, or when we change the height of the GHE, we varied the total number of GHEs so that the borehole area is the same. Meaning, for the reference case of 24 inches, we had 8 GHEs. But for when we decreased the diameter to 16, we used 12 GHEs, or a larger number of GHEs. For the 36-inch case, we used 5 GHEs. And again, for the height case, we also used 12 GHEs, just trying to keep the total borehole area same. Additionally, the 16-inch diameter GHEs and the GHEs that have a height of 13 feet, these are traditionally installed with a 1/2-inch pipe. So the pipe size is 3/4 inch for all these cases except this case and this case, which are 2 additional cases in which the pipe diameter is 1/2 inch. Now we see that for all these configurations, the air source heat pump consumes more electricity than the ground source case. Now, if we take a difference between the electricity consumed, this tells us the amount of electricity that your ground source is able to save in a year. If you take that number and divide it and take the cost and divide it by that number, you get to this figure, which shows the cost per annual electricity saved, meaning how much dollars do you have to spend to save 1 kilowatt hour per year. And based on this parameter, we were able to identify that the GHE case, which is optimum, is the 16-inch diameter and 1/2-inch pipe case. And this case consumes 28.3% less electricity than the air source case. We also looked at the performance of this system over a period of 5 years. And these graphs show the annual seasonal COP in heating in orange and of cooling in blue for the ground heat exchanger case and the air source case. Of course, the air source performance does not change because we've assumed that the climate conditions are not changing from year 1 to year 5. And we see that the optimum system seasonal COP is 36% better than the air source case in heating and 70% better in cooling. Now let's look at the results from Riverside, and I'm just going to directly jump into the cost per annual electricity saved figure. And again, in this case, we also saw that the case in which the diameter is 16-inch and the pipe is 1/2 inch, this was the optimum case. And this case saves about 28.5% or consumes 28.5% less electricity than the air source case. The optimum seasonal COP, although not shown here, is 43% better than the air source in heating and 48% better in cooling. So we come to this part in which we try to incorporate one of the models, which is the simplified capacitance resistance model, and we try to incorporate those modeling results into Energy Plus, which is a building simulation software. Energy Plus relies on G functions, which are response factors, to model the GHEs. We use the improved CARM to generate G functions for a variety of cases, including different soil types, GHE depth and diameter, GHE spacing and arrangement, and number of GHEs. And Mitchell of WCEC and Curtis of WCEC have played an important role in this regard. We have been successful in trying to incorporate it, and we are now working towards Energy Plus simulation for all 16 climate zones of California. So in conclusion, the CARM model was improved using the CFD model. Parametric study of GHE was carried out for different climate zones of California. Response factors from CARM were used to allow Energy Plus to model the helical GHEs, and the results show a significant electricity saving over the baseline air source heat pumps. Yeah, let me focus on one other aspect of the study while people compile their questions.
Sounds great.
And that's that for the Riverside case, because the cooling load was lower, in the reference case, you only needed 5 GHEs, whereas in Honda Smart, or for the Sacramento case, you needed 8 GHEs. But with these 8 GHEs, you come out with a smaller cost per annual electricity saved for the optimum case. That is $4.48 here, whereas for this case, it's $4.74. So it's interesting that how, even though the number of GHEs is higher in Sacramento, you end up saving more electricity, or rather the cost per annual electricity saved is lower for Sacramento than Riverside.
Okay, perfect. All right, well, so today I'm going to talk about a couple of projects that we're working on, and both of them are related to using deep space in some way in order to either provide power or cooling. And so let's dive right into this. So the question we have is, can we produce electrical power from the night sky? Now, at first you might think, well, you know, how do you get power out of the night sky? Now, during the day, you've got the sun, and so you can use the sun's light in order to produce power via the photovoltaic effect, so the solar panels that you see. But at night, you don't have the sun. So how would that work? So that's what I'm going to talk about today. Before I get into that, I just wanted to give a quick overview of my lab. So I'm new to UC Davis, or relatively new. I've been here this past about 8 or 9 months now. And so my lab has a combination of different research projects we work on. Some of them are related to clean energy. And so that's what I'm going to be talking about a little bit today. I'll give a brief overview, one slide of kind of big picture things we work on, and then dive into a couple of projects that I mentioned. We also work with what I'll call quantum technologies. So that's looking at how things work on the nanoscale. So on very, very small scales, how optics are a little bit different there. And there's some interesting electromagnetics and mechanics that occur on this very small scale. And then also with space propulsion. And with space propulsion, what we look at is how you can use photons, so light from the sun or from a laser, in order to push objects around. And you can use that as a way to propel spacecraft. So you can see there's kind of an overall overlying theme that relates to some form of optics, whether it's using the sun for solar energy or for pushing things around, pressure, or looking at how light works on the nanoscale. That's kind of the overarching theme. And so in terms of clean energy technologies, things that I'm not going to really talk about today, but I just want to give you a brief overview. We work on the optics of solar cells. And so if you think of a solar cell, it's a device that deals with both electronics and with optics. So they call that optoelectronics. And we're interested in how we can manipulate the light in order to have lots of absorption, and so you can generate a lot of power that way. That also will affect the electrical properties as you absorb a lot of light. So there's an interesting interplay between optics and electronics in solar cells. So we work on that. We also work on a variety of different types of solar cells. So silicon solar cells are the most common ones. Those are the ones that you'll see on your rooftops. But there's a number of different emerging types of materials, perovskites being one of them. And these are materials that have gone from basically zero efficiency 5 or 10 years ago up to about 20% or over that now. And so the efficiencies have rapidly improved. However, there's still a lot of issues with them. Otherwise, you'd see them deployed. And those issues are mostly related to degradation processes. And so we do scanning probe techniques, which is basically looking at surfaces on the nanoscale in order to understand what's happening during these processes. We also do work with what we call smart windows. So these are materials that you could think of for like a building. I'll show a little video here. They can switch its transparency from either being completely transparent or not, and then also can provide power by incorporating thin photovoltaic layers into it. So that's another technology there. And then finally, we've been doing work on hydrogen materials, which are useful for fuel cells and more traditional things like that. But there's also been a recent resurgence. We've been looking into phenomenon of fusion and lower energy reactions of different types of hydrides. And so this is a collaboration between my group and those at MIT and Lawrence Berkeley National Lab and University of British Columbia. So these are things that I'm not really going to talk about today. So what am I going to talk about? Well, I'll talk about how we're using optics again, one in order to try to mitigate climate change through radiative cooling, and another one for providing power from the night sky. So let's start off with the first one. So in order to get a better idea of where we're going with this, we need to have a little bit of a background. And I think that there's probably a pretty broad audience here. So I just wanted to start off really basic. So hot stuff glows. We all know that, right? If you turn on your burner on your stove, it'll start to glow kind of a reddish color. And we associate that with it being hot. So here's some coals and some ambers that are burning. We've got the sun, this orangish reddish color, also very bright. And this comes down to what we call as black body emission. And so every object will emit light, and that emission of light is related to its temperature. And so here we have a spectral energy density. So it's basically the amount of energy that's being put out from that object as a function of the wavelength of that light. And so as we approach about 6,000 Kelvin, that's about the temperature of our sun, we see that there's a peak in the spectrum, and it's over the visible. And so that's not really a coincidence. Our eyes have evolved in order to see well during the day, in part because that's the light that is illuminating us. Now, if you go to cooler and cooler temperatures, you'll see that the intensity starts to drop off, and also that the peak wavelength here shifts to longer and longer wavelengths. And so these are all still relatively hot objects. But even for cooler objects, so like our bodies, those are, say at 30 C or so, those also are emitting. And so here's an image of a couple of people in the background. So you can see that according to this, their temperature here stands out amongst this background. So even all of us, we're emitting light effectively. So this is very long wavelength light, not visible light, but infrared light. And that's occurring all the time. All right, so that's an important concept moving forward. All right, so getting back to thinking about climate change. And so we're all aware that the overall average temperature on Earth has been increasing, and it's been increasing at a rapidly increasing pace as well. And so in order to try to reduce that effect, people are trying to find ways to reduce the amount of CO2 that's being put up into the atmosphere. And as we all know, burning of fossil fuels is a key culprit that, for why we have more CO2. So as we continue to do that, we're going to put more and more up there. And that kind of traps the heat inside. And so what happens is there's basically there's a balance of heat flowing in and out of the Earth and its atmosphere. And I'll talk more about that on the next slide. But here's just kind of an overview of what that looks like. It's a picture from NASA, and it shows that we've got this incoming light from the sun. Some of it gets reflected off the atmosphere and off the base of the Earth, and other parts get absorbed in various parts. And so there's basically energy coming in from the sun, and there's also some energy going out from the Earth. And it's not really balanced right now. And so if it's not balanced, if there's more energy coming in than going out, then we're going to heat up. And that's exactly what's happening here. So on average, we're absorbing about 1 watt per meter squared more than we're emitting as the Earth. And so I'll go to the next page here. And so here's just kind of pictorially seeing that. So we've got this flux of energy because the sun is basically, it's a black body, as we talked about a couple of slides ago. It's emitting a lot of light. That light, it's energy, right? The photons, they carry energy. That's being absorbed by the Earth. The Earth is also at some temperature. It's not at absolute zero, so it's also emitting some. And so if these things were perfectly balanced, the Earth would just stay this constant temperature. But as I said, it's not. And so one way that people have tried to reduce that, it's a concept of geoengineering. And one idea is that, can you just block some of that light from the sun? And so if you were to do that, then the Earth would absorb less, and you could try to bring it back into balance. And so one of the concerns about doing something like that is, well, how do you do it? And the most common thing that people think about doing is putting basically aerosol particles up in the sky to reflect that light coming in so that it doesn't actually make it into the Earth. However, if you're putting a bunch of aerosol particles up into the atmosphere and let it start to circulate, you might have valid concerns about what that might do to the overall ecosystem and the climate on Earth as well. So I'm not going to go that route. I'm going to ask a different question. Say, rather than blocking some of that incoming sunlight, can we make the Earth emit more? And so how might we do that? All right, well, so I'm going to bring up this concept of passive radiative cooling. And there are materials that can do this. And so the idea is that we want to block the sunlight with this material. So imagine this is, a sheet of paper or something that you can take outside, and it will block the sunlight, so it reflects the sunlight, but it will emit at wavelengths that based on its black body. So that's the concept. So we'd like to have a material that could sit in the sun, but cool down, because it's not going to heat up if it reflects the sunlight. But it could cool down because it's still emitting. Okay, so that's the basic concept. So how do you do that? Well, this comes down to optics again. I said that we like to think about optics, and so it's really an optical problem at the heart of it. So what you want to do is you want to reflect sunlight. So we've got a certain wavelength range here. We want to have a lot of reflection, but we want to be able to emit the infrared. So that'll allow us to cool down. And so these are longer wavelengths, kind of the 10 to 20 microns or so. And so we want to reflect certain wavelengths and emit well at other wavelengths. So if we think about it in terms of absorption of light, we could either have it be transmittive or reflective to one set of materials or to one set of wavelengths, yet strongly emitting for another. And so we can look at that spectral radiance again from the sun. So I showed previously just in this theoretical curve of a black body spectrum. This is what the actual sun spectrum looks like. And so you see that it actually does look quite a bit like that theoretical curve that I showed earlier. So this will lead to heating if you absorb any of this. But if you emit at these longer wavelengths, which is about the emission wavelength of things at room temperature or the Earth's temperature, There's also, it turns out that there's a transparency window in the atmosphere, because the atmosphere, like when you look up, if it's a clear day, like it is a lot of times here at Davis, you see straight out to space. So, you know, you don't have a lot of haziness necessarily. It turns out that for longer wavelengths, though, we can't really see at 8 microns. So we don't really know what it looks like with our own eyes. But you can make measurements, and it turns out that the sky is actually very transparent. The atmosphere is very transparent with these wavelengths. And so that means that if you have an object on Earth that is emitting at those wavelengths, it'll go right through the atmosphere and out to space. If that weren't the case, then it would get absorbed in the atmosphere, and that would kind of defeat the purpose because it wouldn't be leaving. So you can imagine that you can have cooling by emitting at that range of wavelengths. Okay, so I mentioned that you can do this, and so this is really a topic that's come up in the last 5 or 10 years, where people are starting to make these materials that can do exactly that. So here are a couple of examples. I'll just look at one of them here. So here is a sheet of one of these materials, and you can see it looks kind of like a saran wrap, some sort of polymer film here. But if you look at the optical properties, for the visible light, it's fairly transparent, but for these very long infrared light wavelengths that we can't see, it's actually very emissive. And so if you take this material and you put it outside, here's a plot showing that the temperature of those materials can actually start to sink down, and it becomes lower than the ambient temperature here. And so that's a really interesting effect. Imagine going outside and some object cooling down when it's sitting in the sun. Okay, so we now see that there are materials that can actually do this, that can emit light to cool down. And it turns out that the cooling power that they can have is on the order of about 100 watts per meter squared. And so I mentioned to you that the Earth as a whole, it's absorbing about 1 watt per meter squared more than it's emitting. So that's why it's heating up. And so we can say, well, what if we were to take these materials that can emit 100 watts per meter squared and put them over some fraction of the Earth? Could that mitigate this warming trend? And the answer is yes. It'll take about 1 to 2% of the surface area to be covered and transferred to this 100 watt per meter squared emission. But if you were to do that, just kind of systematically put out these little squares, these boxes represent the amount of surface area that you would need in order to mitigate climate change, basically to stop that warming, because you would have balanced out that absorption of the sunlight and the emission from the Earth. You could also take that plot. So actually, I'll say what this plot is. In addition to, you can kind of see the different continents here, but this is also, it's the locally varying amount of power, both absorbed from the sun and emitted from the Earth. And so if these points were all at 0, then we'd be at equilibrium in a steady state, I should say steady state condition where there's no heating or cooling, but it varies throughout the Earth. And if you add up all of these, you find out that we're absorbing a little bit more than we're emitting. Okay, so that's one point of it, is figuring out how much surface area we need. It's also important to think about where you're going to put these. I mean, so you could put these on buildings and things like that, which would be great. But you're going to find that you probably don't have enough space. And so you might want to also look at places where you don't have a lot of population density. So here's a population density map. And so we did another calculation where we looked at, what if you were to take that same amount of surface area and you were to distribute it in regions where you basically have 0 people residing. So there are a couple of deserts here that make good examples. Again, this is not really the way that you would want to do this. You would actually distribute this much more uniformly throughout the globe. But this just kind of gives you a quick idea that, you know, these are feasible concepts that you could use in order to try to reduce climate change. And the specifics here, so I mentioned these, it's about 1 to 2% of the surface coverage. That's about 10 to the 12 meters squared. Next question is, you know, how much would this cost? Well, it turns out that these materials, I showed you some that looked kind of like saran wrap, and so they're relatively inexpensive to make. And so you can make these at about a quarter per meter squared. And so if you were to make that entire area's worth, that's going to be about $1 or $2 trillion. And so that sounds like a lot, but it's only about 3% of global domestic production. And further, there have been predictions saying that, if we were to continue to see this increase in the warming and we get up to about 2 degrees Celsius warmer, then we're looking at about $20 trillion worth of economic loss. And so this is really not that much. And we could also think about it in terms of, right now we're dealing with the coronavirus, which is the most pressing issue right now. But we recently, passed basically $2 trillion in order to help stimulate the economy as a result of having to close down things. So $1 or $2 trillion is not unreasonable to think about in terms of trying to do something that has a global significance. Okay, so then the next part that I wanted to talk about, so we talked about how we can use the night sky in order to cool down the Earth. So I'd like to talk about how we could potentially produce power from the night sky as well. Okay, and so again, we're going to use these concepts of photonics, and we're going to try to figure out a way to generate electrical power on Earth using photonics in deep space. And so one way that we can think about that, we can think about this kind of like a heat engine. And so if you have a heat engine, you're basically looking at a hot body and a cold body, and looking at how you can get power transferred between these two bodies that are at different temperatures, right? And so a solar cell, while it's not a heat engine, you can think about it in some ways like one. And so from that point of view, the Earth over here is the cold body. So we're at 300 Kelvin. The sun, that's the hot body, and that's at about 6,000 Kelvin. And so basically we have just heat being transferred between these two objects that are at different temperatures, and we're using some electronics in order to pick off that energy. And so that's the way a traditional solar cell works. And so I'm not going to go into a lot of details again, because I think we have a relatively broad audience. But it's a semiconductor. We've got a p-n junction device. And what happens is light comes in, it generates electrons and holes. And then when we generate a lot of these charge carriers, is what they are effectively, we get a voltage across the semiconductor. And then we also get current flowing across the semiconductor. And so if we look at this little diagram here, we've got, light is coming in from the sun. It turns out that photovoltaics also emit a little bit of light, but it's absorbing much more light than it's emitting. And we're generating some voltage and some current on it. And the product of voltage and current, that's power. And so that's how we produce power when we have a solar cell out in the sun during the day. Now, we could also think about deep space as being a thermal reservoir. So deep space is really, really cold. So that's at like 3 Kelvin. And so if we think about something on Earth and looking at space, Earth is now our hot object and space is our cold object, but it's still just 2 different temperatures. And so the idea is that if, since all things that are at non-zero temperature emit like black bodies, when we're looking at kind of black body emission between the Earth and deep space, can we pick off that power as well? Because there's just 2 bodies at different temperatures. And so that's the concept that we're looking at here. This is called a thermoradiative cell. And so the idea is as follows. So in this case, we have our solar cell here, although it's not really a solar cell, it's a photovoltaic device. So it's the material itself, it's a semiconductor. It also has a p-n junction. So it's very much operating like a traditional solar cell. So we'll call that a photovoltaic. And so what it does is, because it's hotter than the thing it's looking at, which is space, which is really cold, there's more light coming from this photovoltaic than there is from deep space. And so the consequence of that is the following. So if we take our semiconductor p-n junction again, now, because it's emitting more light than it's absorbing, there are fewer carriers here than normal. And so what that does is it actually switches around. We still end up getting a voltage, but it switches that voltage around, so it now becomes negative. Similarly, because we have fewer carriers, these contacts start pushing charge carriers in. So we get current again, but it's also going in the opposite direction. So by having this photovoltaic working at a warm temperature compared to what it's looking at, we actually get a voltage and a current, but they're both opposite of what they used to be. And so if we go back and we look at a current versus voltage characteristic, and so this is how we determine the power of a photovoltaic. Here's an example of a silicon cell. So when we look at it, we get this positive current and positive voltage based on our sign convention here. And we're generating some amount of power, which is the product of the current and the voltage. With this, this thermoradiative cell, what happens is rather than having the positive current and positive voltage, we now have negative current and negative voltage. So the product, the power, which is the product of these two, it still gives you the same sign. So if the power is positive here, the power is positive here because the two minus signs cancel. And so that's the region where we'd have this thermophotovoltaic working. And so again, we can produce power just like we would with a regular solar cell. And so we've been working on experiments with this as well. So we've been doing things in the lab. We're also looking to move outside to actually use the night sky. But here's just kind of an example of this sort of concept. So you might be asking, well, how well does this work? So it turns out that theoretically, the amount of power that we could get out, if we choose a particular semiconductor that has a very low band gap, in theory, we can get about 50 watts per meter squared of electrical power out of that. And so that's actually quite a bit. A silicon solar cell is producing about 200 watts per meter squared. So it's maybe about a quarter of what you'd get for a silicon solar cell, but this can work at any time. So a normal solar cell only works for about 8 hours during the day. This could work 24 hours a day. So it has some real potential there. If you look at it more carefully and go through a more significant theoretical study of it, you'll find out that there are a lot of things that will start to reduce that theoretical efficiency, as with any sort of material and device. And so it turns out that under more realistic conditions, you can get a few watts per meter squared. And while that's not quite as significant as, say, 50 watts per meter squared, it's still really interesting to think about if you have a low power system that you want to operate at night, that you could use this sort of concept. And you could also think about incorporating it with traditional photovoltaics. And so that's what I wanted to just kind of conclude on here for some of the future directions for this sort of technology. I mean, one is just being able to make this work at night. You know, that's a pretty cool concept on its own. But you could also think about doing it as kind of a daytime and nighttime cycle, where you could use the sun either for heating it so that it could be even hotter than the Earth, or you could put another photovoltaic, or a traditional photovoltaic, a solar one here. So you could use the sun's light for during the day, and you could use one of these at night. And again, since we work with a lot of optics, there's other kind of optical tricks that we could use. There are these things called metasurfaces and flat optics, which allow for very, very thin optical components. And there's some interesting ways in which you might be able to route the light around in these types of devices in order to get hot and cold objects simultaneously. All right, so we started off asking, can we produce electrical power from the night sky? The answer is yes, we can. And so I've shown two examples from some recent work from our lab. One where we're doing exactly this and producing electrical power using these thermoradiative cells, and using a similar sort of concept of radiative emission and radiative cooling. I've also shown an example where you can try to cool down an object locally, which you could expand globally in order to reduce climatic warming. And so with that, I'd like to thank our team. I was going to say I have a picture of the lab and a picture outside the lab, but I guess all these pictures are outside the lab at a barbecue and some other kind of fun activities here. But these are the people that are in there doing the work all the time. So I have to thank them a lot for that. Also thank our funding agencies, which have been making this all possible. And I'll thank all of you for tuning in on Zoom today to hear a little bit about our research. So thank you.
Thanks so much, Jeremy. That was great. And
Hi, thanks so much for your presentation. Really interesting and novel work. I was wondering how the radiative cooling concept that you talked about kind of compares to current efforts that are being used simply to use like reflective materials on buildings to mitigate things like urban heat islands. So things like cool roofs, painting roads white like they've been doing in Los Angeles in some pilots. Like, how does the effectiveness of those types of things compare to these new materials?
Yeah, great question. Yes, I would say that these are complementary, and to some way you could think about these as kind of evolving concepts. So the idea of using something very reflective is good because that does the first part. So the first thing you'd like to do is you'd like to not absorb that solar sunlight. And so for that, you want something really reflective. And I think that for a long time, that's been kind of the focus is can we get materials that are really reflective and just not heat up as much? So that's the first part, is just not heating things up by making them reflective. The next part is, well, rather than just not heating them up, could we actually cool them? And so what this is working with is just a different wavelength range. So the being reflective to sunlight, that's again kind of like the visible range. And so if you look at something white that's scattering a lot of light and it ends up getting reflected back, you basically want to have something that's also operating at a much longer wavelength, which is the wavelengths we usually don't look at. But if you were to use an infrared camera, you would be seeing these wavelengths as well. And so what you want there is you want something that actually is going to absorb a lot or emit. It turns out that these two things are the same, absorption and emission. I didn't want to get into all those details, but basically you want something that's going to absorb a lot in this infrared region. And so some of these materials that they're using for these cool roofs, like the white paints and things like that, some of them actually do have some pretty good absorptive or emissive properties in these long wavelengths as well. But if you start looking at them and starting to engineer the optics of it, you can actually improve them. But I would say that this is exactly the same sort of line of thinking. You're just kind of pushing it to the next frequency range of importance. And rather than just kind of keeping things from heating up, we're now actually going to try to cool them.
Cool.
Good
Thank
question.
you.
Yeah.
Thanks. So this is about your other research topic about the emissive or like the nighttime solar. And I was wondering if these types of materials, instead of just radiating from the Earth to space, which is so it's working on the concept of one thing being colder than the other, could you use this material as some sort of a coating on just like you know, like furnaces or pipes or things that are doing heat, like experiencing heat loss, and be able to kind of get power from like almost like heat recovery from objects that are just losing heat?
Yes, exactly. Excellent question. In fact, that's where these materials were first used for. So the concept of a thermoradiative photovoltaic is actually one that's been around for a while. And so what people have used that for is exactly this, kind of waste heat recovery. So if you have an engine or some sort of object that is significantly hotter than its surroundings, you can put this one of these devices on there and use that to pick off a little bit of extra energy. And so yeah, that's the that definitely works. The reason that people usually don't do that is a lot of times it's not economically feasible for the amount of scavenged heat, because things get so hot there. You also have to be able to have relatively good access to a cold body. And so the nice thing about using this for kind of this nighttime photovoltaic application is that you don't have to worry as much about convective coupling if you design it properly. It's all radiative. And so in that case, then you're really radiating out to space. But yeah, no, excellent question. And that is another application for these materials.